Hello everyone, welcome back to part 3 of chapter 28. Before we continue on with some of the other physics in this particular chapter, I want to go back and discuss this idea of how magnets are actually made, because we've already seen some discussion on magnetic force, magnetic field, but we haven't really talked about where these magnetic fields are coming from or how a magnet is going to be produced. And back in the first video of this chapter, we mentioned that every magnet was going to be polar. In other words, it was going to have a north and a south pole. And so we could say that we have a magnetic dipole in the case of this bar magnet, which has a north and a south end. But we then said that if we cut that magnet in half, we don't produce two independent poles. So we can't just cut this in half and have a north pole magnet or a south pole magnet. When we cut these in half, we just produce two smaller magnets. And if we continue that process in dividing the magnets, we can divide them in half. The sizes of the divisions don't even have to be the same size. Regardless of how we cut up this magnet, each new piece is always going to have a north-south component. So we're always going to have this dipole relationship with those magnets. The question is, how far can you go in dividing up these magnets? What's the smallest piece that you can have that would still be considered a dipole? And in that case, the smallest that you could get would be an atom. So let's consider the simplest of atoms, which would be a hydrogen atom. Our hydrogen atom will have a nucleus made up of one proton, and then we'll have one electron, which is orbiting around that proton. Now, we've already seen that in order for a magnetic field to occur, there has to be a moving charge that is within the presence of a magnetic field. In the previous video, we also talked about how centripetal forces are going to come back into play, and how certain magnetic forces can act as centripetal forces. Well, in the case of our electron, as the electron is orbiting around our proton, it's actually more of an electric force which is attracting the two together. And it is this electric force that not only attracts the electron to the proton, but it is that electric force that acts as the centripetal force in this system. As our charged particle moves, it will produce a magnetic field. And so it's almost the counter statement as to what we saw here. We have one statement that says electric charge in motion let me rephrase this. I'll say an electric charge in motion will be affected by a magnetic field. But at the same time, we can say that a moving, forgot the word charge. So an electric charge in motion will be affected by a magnetic field. But at the same time, we can say that a moving charge will produce a magnetic field. So one term can affect the other and vice versa. And this is where I mentioned in a previous video that electric and magnetic phenomenon are basically two sides of the same coin. We can have electric phenomenon essentially effecting or producing magnetic phenomenon. And then when we get into chapter 30, we'll talk about how certain magnetic phenomenon will influence and create electric phenomenon. So the two are very cyclic when it comes to their relationship. So back to that atom that we have our electron that is orbiting around this proton. As that electron orbits, it's moving, and more specifically, when a charge moves in a circular path, it will produce its magnetic field through the center of that circular arc. So what we have here, I'm going to redraw our atom so that we have more of a side view as opposed to the overhead view up above. So here we have kind of a side view. We can think of our looking at the front planar cut of that atom, and as our electron travels around the proton, it will generate a magnetic field. And that magnetic field is going to have to run through the center of that atom. It has to run perpendicular to the plane on which that electron is orbiting. Now the question is, does that magnetic field point up or does it point down? And the way that we're going to answer that is to, again, use, and I cannot spell today, can I? Should have been side view. We are once again going to use the right-hand rule to help us figure that out. Now we've seen the right-hand rule used in multiple fashions. We've seen the right-hand rule used to define the Cartesian reference frame XYZ. We have index, middle finger, thumb. We've also seen the right-hand rule used for evaluating cross products. So the index finger is the velocity of the charge. The middle finger is the magnetic field. The thumb is the resulting magnetic force. And then thumb. Well, now we're moving in a circle. So how do I get this stuff to actually apply to circular motion? And in addition to that, how do I apply that to these two cases? Because we're basically talking about the same thing, but arranged in a different order. In one case, we say it's the charge that's producing the magnetic field, but in another case, we say that it's a field that's producing charge motion. So how do we figure that out? What do we do? Well, here comes the third method of using the right-hand rule. Whenever we have magnetic fields and moving charges, we're always going to see two things happening inside our systems. We're going to see one of the two, either the magnetic field or the charge, with straight line, I should say straight line direction. I don't want to say straight line motion. And then we're going to see another part of the system with a curved direction. So straight direction means something moving in a straight line. Curved direction means something moving in a curve, or in this case, circular motion. All right. Well, whatever the straight line direction, whatever happens to be moving in a straight line, or rather I should say whatever happens to be pointing in a straight line, you're going to use your thumb to indicate that direction. Whatever is moving in a curved direction, you're going to use the curve of your fingers. So you're going to essentially make a fist with your hand and follow the curve of your fingers. We combine the two, and that tells us everything that we need to know about either of these relationships up here. So we'll give you an example. If I have a circular wire and there is current traveling through that wire in a counterclockwise direction, which way will the resulting magnetic field point? So we come back up here and we say to ourselves, all right, there's going to be two things in this picture. One of the two items has to point in a straight line. The other has a curved direction associated with it. Well, it's pretty easy to see that it's the current that is curving as it goes around in the circle. So the current will be the curved portion. So we're going to make a fist, and we're going to allow our fingers to curve in the same direction as what we see the current traveling. So I'm going to try to draw a hand here with some curved fingers. Put in some knuckles here. So I can't really draw a hand, but we'll just try this. We'll say this is the curve of our fingers, and then the straight portion of this diagram, the only thing left is the related magnetic field. And if you hold your hand right over the screen and you allow your four fingers to curve in the direction of that current, you should see your thumb pointing up and out of the page. And so this is how we associate the direction of current flow to the direction of the resulting magnetic field that is going to be produced. Now, we said up above that moving charge can affect magnetic field, and that magnetic field can affect moving charge. To reiterate that, another way of saying that statement is that current can produce magnetic field. And case in point, right here, we have some current moving in a circle, and we are going to produce magnetic field through the center of that circle that is pointing out of the page towards us. But then we're going to see in a future chapter that we can use magnetic fields to produce current. So how is that going to happen? Well, one way that that can happen is if we can somehow get magnetic field to move in a circle. Now, we're not to the point yet of explaining how a magnetic field would move in a circle, but it's coming. We're eventually going to get to this case scenario where a magnetic field can move in a circle. But if that's the case, well, there should be a current associated with this system. Where's the current? Better yet, where's the wire that's carrying that current? Because over here, the wire that I had was right here in this loop. I already had that current established, and then the magnetic field passed through the center of that loop. But here I have a loop with magnetic field traveling around it, and this loop that I've drawn here, that's not necessarily a wire. That was just there for me to indicate that there was a circular path. Well, go back to the right-hand rule. Right-hand rule says when it comes to current and magnetic field, one of them is going to be pointing in a straight line, the other is going to be in a curved direction. In this case, it's the magnetic field that's in the curved direction. So take your fist, allow your fingers to curve in the direction of whatever is moving in the curved direction for your diagram, which in this case is the magnetic field, and then see which way your thumb pops out. And again, it should be pointing out of the page towards you. And this means that if I have a magnetic field moving in a circular path like this, it should be associated with a wire carrying current through the cross-section of our screen. So the two pictures look pretty identical in terms of what's moving in a curve and what's moving in a straight line, but we've just interchanged the two terms. And the right-hand rule works for both of them, believe it or not. So back up to our atom, our hydrogen atom here. We have an electron that we said was moving in a counterclockwise direction. And so if my electron is moving in this counterclockwise direction, well, we should be able to use the right-hand rule to tell us what direction the resulting magnetic field is going to point. So I'll give you a moment to apply this right-hand rule, this third version of the right-hand rule that we've come up with. So curved portion of the diagram is the curve of your fingers. The straight portion will be the direction of your thumb. And let's see here. So we have our electron moving this way. We put our fingers there. We allow our fingers to curve, and everybody says, "Oh, okay. So my thumb is pointing out of the page. That's going to be the direction of the magnetic field." And well, that is incorrect. But why? Like, we did everything that you did down here. We took the charge with the current going in the circle, and these are the magnetic field relationships between the field and the current. But what's the definition of current? Remember the definition of current? It's the flow of positive charge in your circuit. And what do we have moving around this atom? It's an electron. Electrons are negatively charged. And so if I have an electron that is orbiting around this nucleus in a counterclockwise direction, what would be the direction of positive charge flow? Equivalently. I know we don't actually have any positive charges floating around outside in that electron cloud, but by definition, what should be the direction of current flow with respect to that electron? And it should be the clockwise direction. And we have to use current along with our definition of the right-hand rule. Okay, it has to be a combination of current and magnetic field, and current has to be the flow of positive charge in the system. So with that said, let's try this again. Let's take the curve of our fingers and allow the curve of our fingers to point in the direction of the current flow. So now I have to get my fingers to curve this way, and that means I have to turn my fist upside down so that my thumb points into the screen. And so that is the direction that the magnetic field is actually going to point. And it will point right through the center of that atom. Now, is that magnetic field going to affect the proton? And the answer is no, because with respect to everything else in that atom, the proton should be stationary. The proton should remain at the center of the atom. It shouldn't be moving around. And as long as the charge doesn't move, it will not be affected by the magnetic field. And the reason for that is right here. We need a charge to move before it can be affected by any magnetic force. Okay, so that means that a hydrogen atom can act as a magnet. If we come down here to this side view, we were asking if the magnetic field would point up or down. Well, we know now that the current was traveling this way, and in doing so, we said that the magnetic field had to point into the page. So if we assume that we were still looking down from the top view, then the magnetic field passing through the center of this hydrogen atom would be pointing down. Okay, so it looks like these magnetic fields are being generated by the electron clouds that are orbiting around these atoms. And so that almost implies that every atom that's out there should be magnetic. And to an extent, that's kind of true. But we have to keep in mind that magnetic fields are vectors. And if I have one electron that is producing a magnetic field for my atom, what about other electrons? Because as we progress through the periodic table, these atoms just get bigger and more complex. They have more protons, they have more electrons. So what happens if we move on to the next atom in line? What if we went to a helium atom? So helium has, by definition, 2 protons, 2 neutrons, at least for the most stable isotope of helium. And then we have 2 electrons orbiting around the 2 protons, which make the entire atom neutral in charge. Well, so now we have 2 electrons that are orbiting around the nucleus. So does that mean that the magnetic field that we produce is twice as strong? And it would be, except for the fact that electrons within these orbitals have a property that is known as spin. And what we can do is we can almost take this definition literally, and we can say that one electron will effectively spin in one direction, whereas another electron will spin in the opposite direction. If this happens, we have corresponding currents from each electron that are traveling in opposite directions. And when these currents meet, well, those electrons are effectively traveling around the same radius with the same speed. Their related currents are going to annihilate one another, and we will get a net magnetic field that is 0. And this process continues for larger and larger atoms. We'll just say nucleus here. As we start getting into larger and larger atomic structures, we start seeing multiple orbitals of electrons, and each individual orbital can only house 2 electrons at a time. And you can go through all of the different electron configurations. There's like 1s2, 2s2, 2p6, and on. But for every individual orbital, there's only room for 2 electrons, and those electrons in each orbital have to have opposite spins. And so if we completely fill in an orbital, that negates any net magnetic field that orbital will contribute. So we go through the periodic table. There are some atoms that are magnetic. There are some atoms that are very magnetic. And then there are some atoms that are not magnetic at all. And these all have to do with the electron configurations. Now, we're not going to worry about any of this electron configuration stuff. This is just a discussion to explain why we have larger objects that manifest magnetic properties. So now you take your large piece of iron and you want to turn it into a magnet. Well, how do you do that? You've got all of these atoms inside of your material, and iron is one of those atoms that has a higher net magnetic field. But if we put all of these atoms together, there's no guarantee that the magnetic field for each atom is going to be pointing in the same direction. In fact, most of these are going to be oriented in random directions. And if we take the summation of a bunch of random numbers, we're going to get 0. We need some way of aligning all of these magnetic, what we're going to call dipoles. Because remember, every magnet, no matter how big or small, has that north-south relationship. And we're going to take our hydrogen atom, and the direction that the arrow points for our magnetic field is going to be the direction for our north-south relationship. So how do I get all of these atoms to arrange themselves in at least a fairly reasonable net direction? I may not be able to get all of them to point in the same direction, but maybe I can get the majority of them to point in the same direction. And if I could do that, then I would see a net macroscopic combination that would produce a net magnetic field for that larger chunk of iron. Or it could be something else. There's lots of different materials and composites that can be used to make magnets. So how do I go from this to this? How do I get those magnetic dipoles to rearrange themselves? And the way that we do that is we have to expose this particular item to a very strong external magnetic field. And that external magnetic field will cause these individual magnetic dipoles to rotate and reorient themselves. If you remember, we had an example problem back in chapter 2 that dealt with an electric dipole that was placed inside an electric field. And there would be electric forces involved that would create torque. And this torque would force the dipole to rotate to a new orientation that would align it with the external electric field that it was sitting in. Well, exactly the same thing is going to happen here with these atoms when we expose them to the external magnetic field. We're going to see all of these magnetic dipoles start to rotate and reorient themselves in the material. The problem is, how do we keep them in that new orientation? Because at some point, I'm going to have to take that external magnetic field away. And if I just expose a piece of iron to an external magnetic field, well, it may make that piece of iron magnetic for a little while, but eventually all of these dipoles are probably going to rotate or vibrate into a new orientation that takes them back to a random net magnetic field of 0. And the reason for that is that most of these atoms are already happy with the orientation that they have. Well, we've all played with magnets before, so we know that this is possible to do. So how do you take a bunch of randomly oriented atoms and reorient them and keep them there? So we'll start with the random orientations. I'm just going to draw a handful of these atoms, and we'll put in some random orientations for the dipoles. So no net magnetic field for our chunk of iron right now. But if I could somehow figure out a way of unlocking all of these atoms from one another, because right now there's a lot of chemical bonds that are holding these atoms together in their current orientations. If I could somehow find a way of removing those chemical bonds so that I could then expose this chunk of iron to a very powerful external magnetic field. Then I could rearrange all of the dipole moments within that material so that they're all pointing in the same direction. So we pass this piece of iron through the magnetic field. And then I want to reestablish all of those chemical bonds. So I want to reestablish the chemical bonds between all of the atoms so that they become locked in this new position. And you might be thinking, well, that sounds pretty impossible. How are you going to just magically remove chemical bonds for a bunch of iron atoms? And then how do you expect to reestablish those bonds? Well, we could do that pretty easy just by heating it up. In fact, if we heat up this iron to the melting point, that is when those chemical bonds will start to break away, because the energy associated with each atom is going to be too high for those bonds to be maintained. Now, we don't actually have to get the material up to the melting point. We can just get it really, really hot, and that'll loosen the bonds. So we get this really hot piece of iron, we place it into an external magnetic field, which will reorient all of those dipole moments. But then if we take the hot magnet back out, well, that heat energy is just going to randomize all of the dipole moments again. To overcome that little hurdle, we'll just keep this piece of iron inside of the external magnetic field until it cools. And as it cools, that's when those chemical bonds will reestablish and those dipole moments will lock themselves in place. And then once our material has cooled, we can remove it from the external magnetic field, and we'll have a material that has a net magnetic field all its own, and it'll stay that way until you heat it up again. If you heat up a magnet, it will lose its magnetic properties, unfortunately. So this is one thing that firefighters actually see quite a bit in house fires. They'll be investigating what caused the fire, and they'll walk into the kitchen and they'll see that all the magnets have fallen off of the fridge. And that's because the temperatures got so high that it randomized all of the magnetic dipole moments that were in that fridge magnet, and they fell off. All right, so I think that brings us to the end of what I wanted to discuss for this video. I do have one more thing. It's not necessarily related to how we make a magnet up here, but we do want to talk about the force that a wire will experience as it carries charge through a magnetic field. And we already know that as a charge moves through a magnetic field, so I'm going to put some magnetic field lines oriented into the board. And I have a single charge with its velocity oriented up through this wire. The cross product says that the first vector is the index finger, the second vector is the middle finger, and the resulting vector, or the magnetic force that we're looking for, is going to be our thumb. So we're going to point our index finger up, our middle finger will point into the screen. As a result, our thumb has to point to the left. Oops. There we go. Couldn't get the stylus to change. But that's just for a single particle. What happens when we have multiple particles that are all being pushed up against the wire? Well, in that case, there's going to be some net force acting on the wire. And it's very conceivable that that wire could end up bowing out as a result of that force. So up here we'll have some kind of connection points where our wire is anchored in. So we could end up seeing that wire bow because of the magnetic force. And if that net magnetic force is too extreme, it could literally end up ripping the wire out of its connection. So we want to know what that net force is going to be. Well, does that mean I have to go through and add up every single charged particle that's traveling through the wire? Yes and no. We can actually get away without having to do any fancy integration. We're going to start with the single charge expression for magnetic force, and we want to update this for multiple charges. More specifically, we want to update this for current, because the current already tells us at what rate the charge is moving through that wire. All I need to do is figure out how can I get some kind of time expression to pair up with my charge, because I can't just include time, because if I do that, then I change the expression on the left-hand side. It's no longer force. I don't know what it would be, but well, let's just say I can't do that. So how do I get a time value to pair up with the charge without including a time value on the left-hand side? Well, my only option at this point is to see if I can steal time from one of the other terms that is already on the right side. And velocity, well, velocity does have a time in it. Velocity is supposed to be displacement over time. And in this case, the displacement would be a vector. But what's the displacement going to be? Well, the displacement is the displacement through the wire that the charges have to travel. More specifically, it's the displacement of the wire through the magnetic field. Well, we'll just go ahead and say that that's the length of the wire. And that means that the length of the wire has just become the displacement value that is going to define the velocity of the charges. Let's be realistic. It's not it's not going to be that easy for us to measure the values of the individual charges and the velocities of the individual charges. But it's really easy for us to measure the current. All we have to do is get out our multimeter in the lab. We can measure that current. Plus, we can also measure the length of the wire that we're going to be using. So we now have Q. V is going to be replaced with the L over T expression. We are then going to combine the charge and time terms to produce current. And now we have a new and improved version of the force expression that tells us what kind of force we can expect to get as we move a current through a wire of length L through a magnetic field of magnitude B. Now there's still a dot product relationship here, and so we need to discuss whether or not there are going to be any changes to the method of that dot product. Well, geez, that's wrong of me. I'm sorry. I said dot product. This is a cross product, obviously. I must need some more coffee. So, all right, we have a cross product. And our means of evaluating a cross product is to take the magnitude of each vector times the sine of the angle between the vectors. The current is a scalar, just like charge was. Well, so how is this any different from what we had with the single charge moving through the wire? We have our current moving through the wire, and the length of the wire is now acting as a displacement vector. And if we just say the length of the wire, usually we just think of a scalar value. We measure how long the wire is, but now we have to associate a vector direction with that. The direction of our L vector is the same direction of the current. So technically, even though current is a scalar, current does have a direction that it flows in. The length of the wire acting as the displacement vector will take on the responsibility of indicating the direction of the charge flow. And so with that, we can see that our L vector is pointing up. Our magnetic field vector is pointing into the page. We get our right-hand rule ready. The first vector in the cross product is the index finger. The second vector in the cross product is the middle finger. And the resulting vector is the thumb. So our index finger needs to point up in the direction of L. Middle finger points into the page, direction of field. The resulting force points to the left. And that should not be surprising because this is exactly the same wire as what we had up here, with the individual charges moving through the wire through the magnetic field. Right, so in conclusion, we now have two different ways of establishing magnetic force. We can use the individual charges with their velocities passing through a magnetic field, or we can now apply this to an entire wire carrying current through a magnetic field. All right, that is the end of video 3. When we come back for video 4, we have just a few more things that we want to cover. We're going to look at we actually only have one more thing that we need to cover, which is going to be magnetic force that acts on a wire that is carrying current. And then we need to take that wire and we need to arrange it into some different shapes and see how those magnetic fields and magnetic forces will affect that wire. So see you back for part 4.